So we've now seen how Google Sheets can help us figure out the constant speed of moving objects. For our tumble buggy here, we graphed out the distance and time values of several different trials going different distances and therefore different times, and averaged out the values by drawing a best fit line between them, a trend line, a line that shows the trend between the distances and times that the object is moving. Now, the steepness of this line, the slope, could also be calculated for us by Google Sheets once the line is drawn. So, Google Sheets can tell us how fast the object is moving by eliminating the arrows, by looking at the trend line, and the steepness of the trend line is the speed, because the slope, the steepness, is the rise over the run, which is, in this case, the distance divided by the time, which is speed. Okay? Now, this also means that the steepness of the line should be able to tell us relatively how fast or slow an object is moving. So, for example, if I had a trend line something like this, that would show that in a short amount of time, we cover a lot of distance. So that's a fast-moving object. If my slope is lower, then the object is slower. This flatter, shallower slope is going to tell me that it takes a very long time just for us to cover a very small amount of distance. Okay? So looking at a graph of distance versus time, not only can give you the slope, which is the speed of the object, but it can also help you compare whether you've got a faster or slower moving object just based on how steep the line is. Now, you have to be careful about this because a graph like this can be squished to make a line look steeper than it actually is. So now my tumble buggy looks like it's moving a lot faster than it actually is because I've compressed the x-axis here. You might also have a case where something gets stretched out, like this, which makes your line more shallow and more flat. So at a glance, it probably seems like the object is moving slower than something, say, like this. But in reality, the slope is still the same. If you watch this 0.372, whether I stretch it out or not, the slope is still the same. Now, instead of graphing the speed of a tumble buggy this time, we're going to compare the speeds of bubbles in different liquids that have different viscosities. A viscosity is just a thickness of the liquid. It's the resistance for the liquid to flow. So syrup and honey are common viscous liquids. These liquids have a different viscosity, which means things should move through them at different rates, at different speeds. So I've got a bubble at the top of each of these tubes that's going to move through the liquid at a fairly constant rate. The buoyant force of the air being lighter than the liquid makes it so that it has to travel through the liquid to get to the top, to the highest point, and the liquid's going to settle beneath it. But also, the bubble has to fight through that liquid, so the buoyant force of it rising is going to be balanced with the force of the liquid pushing back against the bubble. Depending on how thick the liquid is, we should get the bubbles traveling at different speeds. Oops. So if I hold these next to each other, you can see that the bubble's moving faster through the blue liquid than through the green liquid. Now, if I want to know how fast they're moving, like in centimeters per second, and also compare a whole bunch of data to say which one is fastest and slowest, I can actually do that pretty easily with graphs. Just depending on how steep the line is can tell me which one is moving faster or slower. So I don't need to actually go through and measure all of the liquids in the lab and all the bubbles moving and things like that. We're just going to process the data that we have of distances and times for a bunch of different bubbles and a bunch of different liquids, and use that to figure out which liquid is the most viscous or the least viscous, the thickest or the thinnest. Here we have the distance and time data for a bunch of different liquids having a bubble moving through them. So the distance is how far the bubble moves in a specific amount of time, like 2 seconds, 4 seconds, 6 seconds, 8 seconds, 10, 12, up to 16, or in the case down here, about every 5 seconds for 40 seconds. If I want to compare how thick or viscous the liquids are, I can tell by looking at how fast the bubble makes it through that tube, where a faster moving bubble is going to cover more distance because the liquid is not as viscous. There's less resistance to flow. So, in order to compare these, I'm going to put them all on the same graph, which means for this set of times that I have here, every 0, 2, 4, 6, every 2 seconds basically through 16 seconds, I'm going to highlight and include all of these distances in centimeters for these three liquids. If I go up here to insert, I can insert a chart just like we've done before. It's just this time I have multiple things that have gone some distance in that specific amount of time. Hey, all right. My graph has already been predicted to be a scatter chart, which is great. Now, if yours does not come up to be a scatter chart from the get-go, like you get a column chart or a line or a pie chart or something like that, you can always go scrolling around to find your scatter chart. Click on that, and you can change it to the type that you need. Okay. I have my distance in centimeters on the y-axis and the time on the x-axis, so that's looking good. So all I have to do now is put trend lines through these and then be able to tell how fast each bubble is going in each liquid by getting the slope of each of those lines. So I'm done setting up. I'm going to go over to customize. I'm going to customize the series, which again is just a fancy way of saying the y-axis. I want to see the relationship between the distance on the y-axis and the time on the x-axis. If I scroll past all the fun stuff, I'm going to click this checkbox on trend line. So I now have a line going through all three of these sets of points. If I go down a little bit farther, I can change the label to use equation so that this will tell me the slope of each of these lines. Now, even without the equation, at a glance, I can tell that our glycol has a faster moving bubble because the slope is steeper. In that same 16-second period, we're covering more distance, almost 150 centimeters. Where in the case of the red line here for our red oil, it's getting a little bit more than 50 centimeters in the same 16-second period. And our yellow line showing the blue oil maybe gets us 20, 25 centimeters in that time. So we've got a pretty slow moving bubble here. So our glycol is the thinnest liquid out of these three, whereas our red line, our red oil, is kind of in the middle, and our blue oil is the thickest. It's the most viscous out of these three. By putting the equation of the trend line on here, this number in front of the x is the slope. It is the rise over the run, the distance over the time. So it is the number of centimeters the bubble travels in a specific number of time of seconds per second. So for my glycol, this 8.86 number in front of the x here is saying that the bubble travels 8.86 centimeters per 1 second. And after another second, it travels another 8.86 centimeters. After another second, it travels another 8.86 centimeters, and on and on and on. Whereas the blue oil only travels 1.28 centimeters every second. So as another second goes by, another 1.28 centimeters is traveled. Okay. Now, this kind of bothers me that my blue oil is in a yellow line and my glycol already has blue on it. So I'm going to switch those a little bit. So I'm going to go back up here. If I click on this line for glycol, I can change the color of that line. So I'm going to do green for this one. Okay. And for my blue oil, I'm going to change it to be blue because that makes sense. Make a match. Do this dark blue there. Nice. So that way, at a glance, blue is for the blue oil, red is for the red oil, and then I've got green for the glycol. Okay? So just by looking at this graph, I can tell which bubble is going to be moving fastest or slowest, and which liquid is therefore thinnest or thickest. Okay? We're going to do the same thing with this set of data down below. So I'm going to grab my graph and scooch it over a little bit. Get out of the way here for a second. So down here, we've got the same kind of setup where we've got time and a whole bunch of distances of bubbles moving through this green oil, this 20W50 motor oil, glycerol, and this 10W40 oil. Okay. If you need to see how to do the graphs, I've got the steps summarized down below here. So you can either rewatch this part of the video where I made this first graph because it works the same way, or you can follow these steps or both. By putting these all in the same graph, we can compare them easily, both by how steep the line is and what the slope of the line is, which is the speed of the bubble moving through each liquid.